and Lyse, if it's okay for you.
Okay, hi everyone. Thank you for the opportunity to be with us today. I am Arnaud BEDDOCK, radiation oncologist in Institut GODINOT, the Comprehensive Cancer Center of Reims, and I am also a AI researcher in a team called AI for Medicine in Crestic from the University of Reims. My main research is on radiomics and image to predict to predict the risk of recurrence after radiation therapy for head and neck cancer. And I have the chance to work with IIAS and Lyse in particular on a project called OptiBoost since more than 1 year. So we will present today the basis to understand what is automatic segmentation in medicine, in radiation therapy, and we will focus after on this project to have a practical case of automatic segmentation. Lyse, if you want to present yourself.
Yes. Hello, everyone. Thank you for being here. I'm Lyse GALLAY, and I'm a data scientist at the Institut d'Intelligence Artificielle en Santé, so IIAS, of Reims University Hospital and Reims Champagne-Ardenne University. My main task consists in developing AI solutions to address healthcare challenges in coordination with the medical staff. So more especially, I'm currently working on the OptiBoost project with Arnaud that we will introduce you in this presentation.
So with this presentation, you will have two points of view. The point of view of a clinician and a physician, and the point of view of a data scientist. So together, we think that you will have all the knowledge you may need if you want to implement automatic segmentation in your research. Do you want to start now, Emily? We can go
start.
ahead.
Yes, we can.
Okay,
go. Yeah.
great. So I will introduce you now the use of automatic segmentation in radiotherapy. You can move to the next slide. Segmentation. So why focus on automatic segmentation? Segmentation is one of the essential steps in radiation therapy planning. It has a direct impact on target coverage, organatrix sparing, and ultimately on treatment outcomes. However, it remains a time-consuming task, and even among experts, there is substantial inter-operator variability. This variability becomes more pronounced as case gets more complex, for instance, with MRI guide for workflow, adaptive treatments, and post-operative target volumes. This situation requires interpretation and consistency, which can be challenging in routine clinical practice. This is why standardization is becoming increasingly important, both to save time and to ensure reproducibility of treatment quality across patients, clinicians, and institutions. In this context, deep learning-based automatic segmentation tools have started to enter clinical routine. They are not designed to replace physicians, hopefully, but rather to support them by providing an initial contour that can be quickly reviewed and adjusted by the clinician. The goal is to combine AI-based efficiency with human clinical judgment. We have prepared for you today some questions to do something interactive. So before we go further, I would like to get a sense of your perception of the workflow. On average, how long does it take to manually contour all organ at risk for a head and neck case on a planning CT? So please select the answer that seems to be most realistic to you. I don't know if we have some answers here.
Yes, we have some answers, and most people, so more than 60%, answer 45 minutes.
45 minutes. Okay. So actually, the correct answer is more than 1 hour. So it's very, very long because we have a lot of to contour them. Do you hear me?
Yes.
Okay, sorry, I just had a little problem. So we have many organs we need to contour. So these organ at risk are organs we need to spare to avoid some toxicity, some side effects. And actually, for full manual contouring of head and neck organ at risk takes between 60 and 90 minutes. So it's very, very long, even when performed by experienced radiation oncologists. This illustrates how time-consuming the segmentation step remains in daily practice and why workflow optimization is such a priority. So now we can move to the next slide. Thank you. So here I present a table with several automatic segmentation tools that are now available in clinical practice, but they are not equivalent. Some are fully integrated into the treatment planning system. For example, RayStation. I don't have any conflict of interest for these softwares, but in this software in particular, uh, it's fully integrated, while others operate as external platforms. Traditional approaches such as those used in MIM, Mastro, or Marida RTX rely on atlas-based segmentation combined with deformed image registration. These methods can be useful, but their performance may vary significantly depending on the anatomy and image quality. Most recent solutions such as mVision AI, Lambus Contour, and ArtPlan are based on deep learning. These models are trained on large analytical datasets and can generate contours within seconds to minutes with more consistent results. So it's very quick compared to the 60, 90 minutes I told you before. However, differences remain in terms of available structures, supported modalities, computation time, clinical validation, and the amount of manual refinement needed. So choosing the right tool depends on workflow, clinical objectives, and local expertise. So another question for now. You can move to the, yes. Question 2, which of the following software provides automatic segmentation directly integrated into a treatment planning system? mVision, MIM Mastro, RayStation, or Limbus?
So again, a question must appear on your screen. You can answer it if you think you have the answer. So I see a few people participating. It's so it's a bit of everywhere. It seems equal between the four answers, but there is a slight upper hand with the first answer, so M vision. Yes. Right
Okay,
now, more than 60% go with the first answer.
okay. So maybe I was not clear with so maybe you can go back to the slide before, the last slide with the table. So maybe it was not clear. The correct answer was here, RayStation. Today, in our TPS, we have only one. TPS treatment planning system that fully integrates directly in the system the deep learning solution. All the others are very interesting, but it's not the deep learning clearly completely integrated in the TPS. What does that mean? That means that the contours are generated in an external software and imported from this external software to the TPS. So we have many 1, 2, 5 minutes longer than recession or in which everything is fully and directly integrated in the TPS. Okay, so next slide. So now we know the tools, we know the softwares, and we know what we can do with these softwares. The question now is what defines a good automatic segmentation? To evaluate whether an automatic segmentation is truly useful, geometric metrics alone are not always sufficient. The dice, maybe you know the dice coefficient, for example, measure how similar two contours are and values around 0.8 or higher are usually considered good for well-defined organs. We have also the Hausdorff distance, which provides additional information on the largest deviations. However, from a clinical perspective, what matters more is whether the contours can be used without significant correction. A contour with high DAC may still require considerable modification, making it inefficient in practice. This is why clinical acceptability and correction times are ultimately the most relevant evaluation. Ultimately, the most relevant evaluation is the dosimetric impact. If an AI-generated contours leads to similar dose distribution and organometry sparing compared to manual segmentation, then it is effectively clinically usable, even if its geometric metrics are not perfect. This is why dosimetric studies are often more informative than geometric statistics alone. So you have here all the step, because you usually just one word, please. If you can go back on the last slide before the question. No, just before the question, I'd like to add something. Yeah, thank you very much. So you have here the different steps. I mean, usually when we try to measure the efficacy of an automatic segmentation tool, usually the first step is to check the geometric performance, the dice, the Hausdorff, etc. We have many other metrics, but it's maybe the most used. But what I want to say to you is that even if we have good performance, good geometric performance, sometimes it's not enough. And the best tool is the one who has been clinically and dosimetric who have a clinical impact and a dosimetric impact. And it's important because in many research, in many studies, you have the geometric performance, but you don't have the clinical and dosimetric study. And sometimes you can have it seems to be a very useful software, but it's not useful in clinics. Okay, so question 3 now. Which of the following values correspond to a very good dice performance? The response A 0.62, B 0 to 73, C 0 to 81, and D 0.45.
Okay, so I don't know if you can hear the alarm. Sorry if it's a bit bothering, but currently I'm seeing half of the people have answered. So you can go ahead and answer to the survey, the question on your screen. Okay, so there is one answer that stands out the most. It's the answer C, 0.81.
Yes, so exactly. This is a good answer. So usually, and maybe Lise, you will confirm after, but usually when we have a dice more than 70%, 75%, basically if we have less than 75%, we don't accept this algorithm, and we try to have a better performance. When we have something more than 75, 80%, that means that seems to be enough good to be tested, and to be tested in with a clinical and dosimetric point of view, as I told you before. Next, so in this figure summarizes a multi-center evaluation published in Frontier in Oncology 2 years ago. The study included 60 patients across 3 anatomical regions: head and neck, pelvis, and thorax. For each case, automatic contours generated by different software solutions were compared to a reference contour set established by a consensus of expert radiation oncologists from the French, Italian, and ESTRO, the European Society Radiation Therapy, contouring groups. The evaluation used 2 metrics: the DICE, measuring geometric overlap, as I told you, and an independent clinical acceptability scoring performed by experienced physicians. So that means the physicians can say the contour is enough good, with a scoring between 1 and 3. The yellow bars here correspond to relatively simple organ at risk, such as the parotid glands or kidneys. For this structure, all methods perform well, with DICE above 85%. The differences become more pronounced when evaluating complex structure, represented here in blue, such as the mesorectum and the medulla oblongata. Deep learning-based tools, particularly Envision AI and Artplan, maintain performance above the commonly accepted clinical threshold of 80%. RayStation and Nimbus show slightly lower but still usable values in the range of 75 to 78%. In contrast, Atlas-based solutions such as MIM and Mirada exhibit more substantial drops, often below 75% for complex anatomies. So the key message here is that performance differences between tools are small for simple structures, so for instance parotid, but becomes clinically relevant for anatomically irregular or postoperative targets, where deep learning models offer a clear advantage. So next question. In which clinical solution in human review particularly important? The heart, the parotid, spinal cord, bulb or mesorectum, or lungs?
So again, if everyone can maybe guess the right answer to this question, you have the survey on your screen. Okay, so a bit of everything. Let's see. Okay, it's very disparate. Let's wait maybe for other people to answer and see if there is one answer that stands out. Right now we can see it's equal between heart contour and spinal cord bulb and mesorectum.
Okay, so I can't see the answers here, but The correct answer is actually C, spinal cord bulb or mesorectum. So these
It's the one that
structures,
stand out. In the end, it's the one that stand out. So you were right.
perfect. So that means that you understood what I told you before. These structures are complex and often difficult to distinguish, even for expert radiation oncologists. Automatic segmentation models tend to show higher variability on these regions. And more importantly, an error of just a few millimeters on the spinal cord, bulb, or the mesorectum can lead to a clinically significant overdose. And again, this evaluation is the most important before using a software, this kind of software in routine clinics. Okay, so next slide. So up to now, I have a focus on organ at risk because actually the software we are using in clinics in routine currently are very useful for organ at risk. So healthy tissue we want to spare to avoid SF side effects. We have some software um, uh, we can use to automatic delineation for the target volume, but it's not very useful. It's not completely useful to treat a patient. But we have a lot of studies in research trying to improve this automatic segmentation for the target volumes. And in these tables, I summarize the mean deep learning studies published over the past years on automatic tumor segmentation in head and neck cancer, especially for the oropharynx. So we have three important messages here. First, most studies focus on the oropharynx and mainly on the GTV. So the GTV is a gross tumor volume, is the volume we can of the tumor we can see without the taking into account of the microscopic disease. And this majority, the majority of these studies target oropharyngeal tumors and almost all focus on the GTV or the competency, the GTV tumor or GTV node. This means that the evidence is concentrated on a relatively favorable site where anatomical contrast is higher and imaging is often of good quality. We still have very few models for other head and neck such as larynx, hypopharynx, or oral cavity, where anatomy is more challenging. Second, inter-observer variability is rarely considered. A major limitation is that most datasets rely on a single annotator. Very few studies include several other observers or measure inter-observer variability. This is important because if the ground truth itself is uncertain, the model may learn that uncertainty. It means so it's very important to have these different contours. And third, performance DICE is generally good. You can see in the last column on the right, most studies report DICE value around 85%, which is very encouraging and consistent with what we expect for GTV segmentation in head and neck. However, these test sets are extremely small, often 10, 20, 25 patients. And I think that Lyse, you will explain after the importance to have a testing cohort and to testing the algorithm on a completely external data set before to implement it in clinical software. Maybe we have a question before to move on. Just before in the chat, I see a question.
Yes, there is a question by Anas. We can answer it right now, or you can wait for
So I
genetic
propose
one?
I have just two slides, and after we can answer some question before to let Liz continue. So the question I prepared, question 5.
There it
What
is.
is currently the main clinical benefit of AI-based automatic segmentation? Completely removing human review, generating a treatment plan without the radiation oncologist, speeding up the definition of organ at risk and simple target structures, or automatically segmenting rare tumor lesions. So what do you think?
Yes. So this is the last question. So if most people can try and give an answer. Okay. So 7 people answered. Okay, it's going up. So there is one answer that really, really stands out. It's the answer C.
So great, it's the good answer. The main clinical value of AI-based segmentation today is not to eliminate expert or to automate the entire treatment plan. We are not there yet, and in fact, we should not aim for fully autonomous planning at this stage. Where AI really brings value is in accelerating routine segmentation tasks that are time-consuming but well-defined, especially organ at risk and relatively simple target volume. For these structures, modern deep learning models achieve very high geometric accuracy, often with dice value above 85 to 90%. This means that the clinician can focus more time on the complex parts, refining difficult cases, checking small critical structures like the medulla or brainstem, and adjusting the tumor volume when it's necessary. AI reduces workload, but expertise remains essential. So before we move on the technical part with Liz, I'd like to make one last point. So what we call automatic controlling is never magic. The performance you get in clinical routine depends directly on how the model was trained, the size of the dataset, the number of observers, the quality of the contours, the imaging modality, and even the type of neural network. This explains why some structures perform extremely well, while others, especially small, irregular, or poorly contrast ones, remains more challenging. To understand where these differences come from and what the technology can and cannot do today, Liz will now walk you through the technical foundation of automatic segmentation. Maybe just we can answer to the question before to Liz move on. So the question is, I want to ask you about Mirada shows a significant drop in performance for complex structures. Could this be attributed to the absence of deep learning? So yes, it's a possibility. We know that, and maybe Liz, can answer to this question after. But clearly, we know that we don't know, but we have seen that using deep learnings, the software that use deep learnings are usually better than the other one who use only atlas-based segmentation. So if you want to add something for the technical point of view, Liz, and go go ahead. Thank you very much.
Thank you, Arnaud. So in the second part, we'll go from the early days of artificial intelligence to famous modern architectures for medical image segmentation like UNet and transformers. So my goal here is not to make it too technical, but to help you see the big picture of how each generation of models helped to develop the next one. Next slide, please. Perfect. So before we dive into modern AI methods that can segment tumors or outline organs automatically, let's step back and see how we got here. How deep learning for image segmentation emerged. So AI officially started in 1956 when scientists at Dartmouth College imaged machines that could think. 1 year later, in 1957, Rosenblatt introduced the perceptron, the very first computational model inspired by the way neurons work in our brains. So it could make very small decisions by taking an input, as we can see here, and applying weight on it, just like a simplified neuron. Then in 1986, multi-layer perceptron with backpropagation were introduced, allowing networks to learn from their mistakes. So this was the birth of artificial neural networks, or ANNs, in the following. So ANNs can be trained using supervised learning. So during training, the model is shown examples, inputs, along with the correct answers, the labels. After producing a prediction, the network compares it to the targets and computes a loss or an error, as we can see in this image, which to quantify the error. Then backpropagation is used the loss to update the model's internal parameters, so the weights of the model. The error is propagated backwards through the layers, and each weight is adjusted according to how much it contributed to the final error. By repeating this process over many examples, the network gradually learns to associate inputs with the correct outputs. So multi-layer perceptrons are adapted for a classification task. For example, will this patient die in the last 20 days? So on tabular data, but not for image analysis. We can go to the next slide, please. So a big step forward came in 1999 when Yann Lequin developed LeNet5. It introduced the first convolutional neural networks, or CNN, to recognize handwritten digits. So as we can see here, a CNN has two main parts, the feature extraction part and the classification part that use a fully connected multi-layer perceptron. So it's at the end of the network for classification of extracted features vector. If we focus on the feature extraction part, CNN work by automatically detecting visual patterns in an image. They do this using convolutional kernels, which are very small filters that slide over the image. So each filter reacts to a particular type of pattern, such as edges, colors, or simple textures. And as these filters are applied layer after layer, the first convolutional layers typically detect low-level features, such as edges and textures, while the deeper layers capture more complex and abstract patterns and structures. So learning consists in adjusting the kernel values, or the weights inside the kernel, to hierarchically extract features from the input data. This worked so well for natural images that researchers quickly asked whether it could be used for medical images. But most of the time, the medicine needs more that recognition. It needs very precise localization, for example, knowing where the tumor is. We can go to the next slide to reach the core of this section, the image segmentation. So segmentation means that the AI doesn't just say there is a tumor, it labels every single pixel or voxel to outline it exactly. So around the 20s, faster GPUs and bigger datasets made deep learning truly possible and helped to develop CNN for segmentation. Next slide, please. Perfect. In 2015, UNIT was the first architecture built specially for biomedical segmentation. It uses an encoder-decoder structure. The encoder, like the feature extraction part of a CNN, extracts the main feature, while the decoder part rebuilds a full resolution segmentation mask. So some skip connections pass fine details from the encoder directly to the decoder, so nothing is lost, as we can see here in the image with the concatenate part. UNIT works even with small data sets, which is perfect for medicine where labeled data is limited. After 2015, most new models were variations or improvements of this U-shaped design. So 1 year later came VNet, a 3D version of UNIT. It processes full volumetric data like MRI or CT scans using 3D convolutions. It's important to distinguish multi-channel 2D data where all channels correspond to the same spatial localization from true volumetric 3D data in which each slice represents a different spatial position. So for multi-channel 2D data, we can simply apply 2D kernels as in the traditional units, and we can apply them independently on each modality and concatenate the results. In contrast, 3D convolutions are designed to capture spatial context across volume slices. So this apart, VNet excels in tasks like organ segmentation, but it's heavy to compute. Hence, it is possible to train it on small 3D patches instead of whole volumes to save resources. In 2018, UNIT++ refined the idea of UNIT skip connections by adding nested ones. This helps link encoder and decoder layers more smoothly by reducing the semantic gap. So that's to say early encoder to late decoder, for example. So it captures small details better, like tumor boundaries. It improved accuracy on many 2D medical data sets, though it required more computation. Then came NN UNIT in 2021. That's called the No New UNIT. It doesn't propose a new architecture, but an automatic system that configures itself depending on the data. It chooses whether to use 2D or 3D, adjusts preprocessing, and sets training parameters by itself. Without any manual tuning, it often outperforms hand-designed models. It's an open source tool that became a reference in medical segmentation, and that's used in a lot of benchmark studies. So CNNs are great for local details, for example, at pixel level, but they struggle to see the whole picture and its global context. They only have a local receptive field and can miss anatomical relationships or long-range dependencies. For example, how distant parts of an organ relate to each other. So in order to model global relationships, researchers took an idea from natural language processing, transformers. So proposed in 2017, transformers rely on what we call self-attention, which means every element can interact with all over. So, for example, the words in a sentence, in order to determine which are most important for understanding the sequence. So the first words of the sentence can then interact with the last words of a sentence, which was not possible with the traditional models without the self-attention. Multi-head attention, that is presented in this image, on the other hand, performs several self-attention in parallel, each examining the sequence from a different perspective. So, for example, one head for meaning, another for position or long distance relationships. Thus, each head captures a particular type of relation. Here we can see that the model then combines all head results to achieve a better understanding of the context. And then after the step, we can pass in a multi-layer perceptron head for the classification of the extracted hidden states. That when transformers were adapted for images, we got the vision transformer, or VIT. So it splits an image into small patches, which are treated as tokens for the attention mechanism, similar to how a sentence is split into words in natural language processing. The main disadvantage of such a method is that it requires a lot of computing power. So most of the time we can use it on with pre-trained models and retrain it for a more specific task. Researchers also try to find solutions to limit the complexity, and then they created the Swin transformer that introduced window-based attention, where attention is computed locally inside windows, so that these windows group several patches. And then we have an iteration where the window slides at each layer so that patches of different windows can interact. So it makes VIT faster, and in case of limited resources, we can still use the transfer learning. In 2022, SwinUNet is proposed for segmentation, mirroring the UNet structure entirely with Swin transformer blocks. It achieved state-of-the-art performance on CT organ segmentation. We have to keep in mind that full transformer architectures no longer use convolutions, which can make it harder to capture local spatial information. Consequently, several hybrid architectures have been proposed that combine convolutional layers with multi-head attention, such as hybrid UNet transformer models. So to conclude, in recent years, deep learning has profoundly transformed image analysis, particularly in segmentation tasks. Modern architectures such as NNUNet and transformer-based models have now become the reference for applications like tumor segmentation. So now I let Arnaud follow with the introduction of the OptiBoost project.
Okay, thank you very much, Lyse. Maybe just before, if you have some questions regarding all this large introduction, you have now all the knowledge you need to understand what we will present about the OptiBoost project. Do you have any question? You can use the chat, or you can You can speak if you want.
Yes, there is also a Q&A section at the bottom, but if needed, you can also speak. We will grant you the rights. But if no one has questions, you can always type them somewhere in this webinar, and we will address it during the Q&A segment at the end of the webinar.
Okay, so maybe I have one question for you, Lyse, before to move on the Optibus project. With my so I have many projects ongoing to create algorithm delineation software in head and neck, and one of the main the main question, the main issue we have is before to start the development of the algorithms and to create the data set for the input. I mean, it's very long and time consuming to delineate all the contours for OptiBoost. You will present the number of patients we need, and we have for head and neck for my head and neck project. We are actually now 4 radiation oncologists delineating more than 300 patients. So it's very long. And my question is, so I have 2 questions. The first question is, how many patients do we need for the training, and how many patients do we need for the testing?
Yeah. So in fact, it depends on the difficulty of the task and of the type of image we use for the training. So we can have a hint of the number of cases we need by looking at research papers, because most of the time that they conclude whether the number of cases was sufficient or not. But more generally, I have a tendency to say that when we have at least 300 positive patients and then at least 300 negative patients, it's very comfortable for deep learning. Then it's the case when we have a single image per case. So when we are working with volumetric data, as in our case, we have a lot of slices per patient, so it multiplies the number of images, and then we can say that around 100 cases are sufficient, and it's a good start for deep learning to have 100 cases.
Okay, great. And for the testing cohort?
Yeah, sorry. So 100 cases in totality, and most of the time we use 80% for the training cohort and 20% for the testing cohorts.
Okay, so 100 in total.
Yeah, exactly.
Okay, it's good to know, because it's very long to create all these contours, and it's clearly mandatory before to start the development.
Yeah, of course. And
okay.
It takes a lot of time, so it's possible during the project to start maybe with less patients to see the results, and then to adapt and to ask more annotations to the medical staff.
Thank you very much. Okay, so if we don't have any other question, we can move on the Optibus project. So thank you very much to IIAS, because my project was nominated 1 year ago. Once it was selected one year ago, and I have the chance to work with Lyse since 1 year on this project. So I will present the objective, the background and the objective of the project, and Lyse will explain to you what we are doing. So breast cancer remains the most common cancer in women worldwide and a major public health concern. According to the GLOBOCAN 2020 estimates, around 2.3 million new cases are diagnosed every year, representing only 1 in 4 cancers in women, with nearly 700,000 deaths globally. In France, the most recent IIAS reports confirm the epidemiology, with more than 61,000 new cases and 12,000 deaths each year. Despite these numbers, the prognosis has significantly improved over the past decades. The combination of earlier detection through mammography, modern systemic therapies, and major progress in radiation oncology now leads to an overall survival close to 80% across all stages. This improved survival has shifted the focus from solely achieving oncologic control to preserving function, quality of life, and cosmetic outcomes, very important in the breast cancer. This shift is central to the motivation behind projects like OptiBoost. So given these therapeutic advances, breast conserving treatment has become the standard approach for early stage disease. So breast conserving treatment means we don't do mastectomy, we conserve the breast. The landmark randomized trials from ERTC and CALGB clearly demonstrating that postoperative radiation significantly decreases the risk of local recurrence and improves breast cancer-specific survival. So a patient has surgery before, at the beginning of the treatment. The first treatment is surgery, is breast conservative surgery. And we know now that if we use radiotherapy on the breast after the surgery, the outcome is better than without radiation oncology. So we have a meta-analysis pulling over than 10,000 patients that showed a reduction by half in any recurrence at 10 years and meaningful improvements in long-term mortality. So adjuvant radiotherapy is not simply an optional component, it is one of the pillars of modern breast cancer care. But today, the key challenge is not longer only to irradiate again, but to irradiate precisely with the smallest possible impact on long-term quality of life. And this is exactly where the delineation of the boost volume becomes critical. So you can go to the next slide. So after breast conserving surgery, what do? We do whole breast irradiation. We irradiate the whole breast. It is recommended for almost all patients. And for some patients, for instance, younger than 50, an additional boost to the tumor bed is systematically advised because it provides the greatest local control benefits. So a boost is when we add a dose in the tumoral bed where the tumor was before the surgery. Accurate delineation of the CTV boost is essential, especially in younger patients who benefit most from optimal local control. So in daily practice, contouring the boost is far from straightforward. The conventional method relies on surgical clips, on preoperative imaging, and on clinical or pathological data. Despite this multimodal information, the delineation remains highly operator-dependent and time-consuming, with significant under-observability, as demonstrated in several studies, including ours. We did actually a study when we compare the IOV, the inter-observability, using different methods to contour this CTV boost. And we obtained between 60 to 70, 80% of dice. So the methods, the IOV depends on the method, but clearly in clinics today, we have a very high IOV when we contour the CTV boost. The problem becomes even more important in patients treated with preoperative systemic therapy. What does that mean? That means that before to be operated, the patient has a systematic therapy. It's recommended for patients who have a very high risk of recurrence after the treatment. When a pathological complete response occurs, in this case, the original tumor location can become unclear, and clips placed before chemotherapy may no longer correspond to the true extent of the tumor beds. These inversities have real clinical consequences. A recent publication reported that up to half of local occurrences arise outside the planned boost volume, suggesting that current methods may not always capture the tumor bed accurately. As a result, clinicians frequently tend to draw larger volume to avoid a geographic miss, but this systematically increasing the risk of late fibrosis, which is the main late toxicity and has a strong impact of long-term cosmetic and functional outcomes. This is precisely where artificial intelligence can help. So automatic contouring has the potential to fundamentally improve this process. Now you know that it can reduce the interoperability that plus current manual definition, offer a standardized and reproducible approach to boost definition, and save time for clinicians while maintaining or even improving accuracy. AI may be especially impactful in post-chemotherapy cases where the tumor bed is most difficult to identify. Ultimately, this can support more consistent and personalized treatment planning. So now, Lyse, if you want to explain what we are doing in this OptiBoost project from a technical point of view.
Yeah, of course. So in that part, as Arnaud said, I will present the main steps of the technical workflow for the OptiBoost project. So everything has been developed in Python, a language widely used in data science projects, notably because it provides many reliable libraries for working with medical images. So the first step of the project consisted in reading the medical data. So each patient's case came with a 4-image series provided by physicians: the preoperative CT, preoperative PET, post-op CT, and the mask. So the boost zone delineated by the medical staff. And that's to say the ground truth. So we want the model to train on for prediction. These data were stored as DICOM files, one file per image slice, using the Python libraries like PyDICOM and Simple ITK, where we read the list of DICOM files for each series based on DICOM metadata in the correct slice order and in a common direction. That's very important, for example, from top to bottom of the body, for example. The 3D volumes were then reconstructed from the slices, and finally, the corresponding masks were loaded in the exact same slice directions as the CTs and link to post-op CT. At this stage, we simply go from fragmented DICOM files to coherent 3D volumes. So as we can see, the images are out of sync between the preoperative images, as we can see, the two first images, and postoperative image, that's to say the third one. Then let's pass to data registration step. For 3D deep learning models, all input channels must share the same spatial position. That means that the preoperative CT must be aligned with the postoperative CT. So these registrations were manually done by the clinicians and were stored inside 2 DCOM files, one for rigid deformation and one for deformable transformation. Simple ITK library uses the same coordinate system as DICOM, which facilitates the registration process in the code. So we load both transformations, we combine them, and apply them to the pre-op volumes using a very useful function that's called simple ITK resample. As we can see here, the result is a perfectly aligned pair of PET and CTs ready for processing. So, yes, we can, perfect. Before using the volumes for machine learning, they must be cleaned and standardized. So, the first step consisted of creating a patient's body mask. So on the CT scans, a simple threshold could give a good approximation of the body parts. In this zone, we kept the largest connected region and filled remaining holes. Because all scans are registered, this body mask could be reused for the 3 volumes of the same case. So, and concerning the pixels outside the body, they were converted to standard background values according to PET and CT pixel units. Then all volumes were resampled to an isotropic voxel size using linear interpolation. The initial resolution could be read in DICOM files, so we used it for the linear interpolation. And this step was very important because we need to have the exact same quantity of information in voxel to facilitate the convolutions. We then processed volume size by standardizing it because deep learning models like UNet benefit from a fixed input dimension. So we created a function that automatically crops or pads the image to reach a common shape. In that case, each voxel continues to represent the same physical space thanks to the previous resampling. Then all values were clipped to medically reasonable ranges to eliminate outliers and to focus on the useful ranges. Following that, a min-max normalization was applied on pixel values, and that's also a very important part, so that different units, such as for TEP and CT units, become comparable. Then, clean volumes and masks were finally saved as compressed nifty files, easily rereadable using simple ITK library. Here, we got the clean data, as we can see example here. So with this clean data, we could go to the next step, that are the steps of the AI parts. So they have not been implemented yet, but we already know which process and best practices we will have to put in place. So I will present them succinctly. So firstly, we would like to experiment data augmentation to have more cases with positive pixels on the mask. But this is very delicate in medical field because we must generate examples that are enough to slightly enrich the data sets without losing realism. So our plan is to use only very minor transformations. So we rearranged these parts from the moment I created the slices because I talked with Arnaud, but we will apply some symmetry and maybe a zoom, but the rotations are even the translations are not really logical, because the scanners will always place the body of the patient at the exact center of the image. So we need to generate cases that could exist in reality. So it's not really logic to use small rotations or translations, but some flips or zoom can be very useful for this part. So let's finish with the major part, with what is planned for training and evaluation pipeline. So to avoid bias, the datasets need to be split into training and test sets, the last one needing to be completely untouched until final evaluation. We will ensure that each patient, that's to say original case or augmented case, appears in only one split, so the model cannot cheat by seeing similar data during training and testing. In our case, we will have 58 patients for training and 20 patients for testing. On the training set, we use cross-validation to estimate how well each model generalizes. We split the data into k folds, using one fold for validation and the rest for training, and repeat this process k times so that each fold serves as validation once. This reduces the risk of getting lucky or unlucky with a single split. For each experimented architecture, this produces K models, and we can average their performance for a more robust comparison. We'll use the very useful group K-fold function from scikit-learn library to create the folds, because it keeps all data from the same patient together, avoiding data leakage. For training parts, we can use libraries such as Keras and TensorFlow that easily help to define our neural networks and train them efficiently on GPUs. A little additional tip is that the flow from directory mechanism ensures that only batches of data are loaded at a time, preventing memory saturation. So once the best architecture is selected, it can be retrained on the totality of the training sets and finally evaluated on the independent test sets. That ensures that no problem occurred for training of that final model that could potentially be used in reality. A last word about segmentation evaluation metrics that were already introduced by Arnaud in its first slides. So it's important to remember that in medical segmentation, classes are usually highly imbalanced with a large background and a small region of interest. That's to say, in our case, a small region for the boost part. So evaluation metrics should be chosen with this particularity in mind, and ideally metrics that complement each other should be used. For example, the DICE score, which measures the overlap between the predicted mask and the ground truth, is widely used because it penalizes both missing areas and false positives. However, DICE does not capture all aspects of segmentation quality, particularly when the shape or distance between contours are important. So the Hausdorff distance can be used additionally to measure the maximum distance between the predicted and true contours. It complements the DICE because DICE can be high even if a small segment is located far from its true position. So to sum up, there were the key points of that last section, and I let Arnaud finish with the key take-home messages.
Thank you very much, Lyse. Okay, so to conclude, the delineation of the boost volume remains one of the most variable and clinically impactful steps in breast radiotherapy. Inter-observer variability is high, and current methods do not always ensure accurate coverage of the tumor bed, especially after preoperative systemic therapy. Artificial intelligence now offers a real opportunity to standardize this process and reduce variability and save time without compromising clinical quality. But to be useful, an AI model must be trained on high quality data and validated in real clinical workflows. This is precisely the ambition of this project OptiBoost, developing and clinically validating a reliable, reproducible tool that can support routine breast radiation oncology and ultimately improve patient outcomes. So we have finished for this presentation. Thank you for your attention, and we are available for a few questions if you want.
Yes, exactly. If you have any question, if you need clarification on certain subject, don't hesitate. You can use the Q&A section or the chat. So yes, don't be shy. It was a long presentation, by the way. Thank you, Dr. BEDDOCK and Miss GALLAY. I'm sure maybe there is some subject you want to talk about again. Don't hesitate. Very welcome.
So maybe just if we don't have a question, just to thank you very much, Lyse, for your presentation. And you have demonstrated here in your presentation the importance of the preparation of the data. We started to work together more than maybe 9 months ago, maybe 1 year, I don't remember, and we didn't start yet the training. So all the steps of the data preparation takes time, but are very, very important.
Yeah, of course. Most of the time we say that the data preprocessing part and data discovering part is about more than 80% of the work. Yeah, it's very important because the model will base all its training on the quality of the data. So we have to take time for the data preprocessing part.
Okay. Thank you very much. Thank you for your attendance, your questions, and your attention. I think you are going to stop for today.
Can I just add
Yeah,
something, Emily?
you can ask.
Okay,
Yeah.
thank you very much. So if you are interested in automatic segmentation and the broader role of AI in radiotherapy, I like to highlight an international course we are organizing with Unicancer Formation on January 15, 2026, in 2 months at the Donelio Innovation Hub in Switzerland. It's an international course in English. The course is called AI in Radiation Oncology from Foundation to Clinical Integration. It is officially endorsed by the European Society for Radiation Therapy and Oncology. It's a Calliope certified, which means financial coverage may be possible through your employer or training organization. And we're also in the process of obtaining European CME accreditation. The course will explore not only technical aspects like contouring and predictive modeling, but also ethical, legal, and economic challenges of implementing AI in clinical practice for radiation therapy. It's designed to be interactive, multidisciplinary, and highly relevant for clinicians, physicians, researchers. So don't hesitate to join us for this course. I'll post in the link in the chat the link to register and look the program. So don't hesitate to reach out me if you need any information. Thank you, Emily.
And I will send you all the information